In the last example, we looked at positive a squared. Okay, so this was giving us positive 3 squared, 3 squared positive. What about 3 squared negative? Okay, so what if we had x squared minus y squared equals negative 4? What's this going to look like? Well, we already established that the a value has something to do with kind of like the hyperbolic radius, the distance from the center. Okay, and in fact, it is the distance from the center to the vertex. So what does this look like? Well, first of all, I want to just point out that if I have x squared minus y squared equals negative 4, it is the same as switching the y and x. So reversing the subtraction and making it positive. Okay, and just so that we're clear on this, if I have 5 minus 3 equals 2, I know that if I reverse the subtraction, I'll get the opposite. Okay, so I can get rid of this negative 2 by reversing the subtraction. Okay, so what's this look like if I do this on a graphing tool? Well, let's do this. You can put in your graphing tool, but I'm also going to show this algebraically. So what happened? So before we checked our domain restriction. Okay, we checked our domain by just testing out this. I'm going to do the same. So I'm going to get x squared is equal to y squared minus 4. Now I have to analyze this expression. The x squared can be 0. Yeah, that's true. I can do 4 minus 4 get 0. And the x squared can, as this y grows, x can get to any number, essentially. So the x squared can be 0 and bigger. That means that x itself can be negative squared and it'll be 0 and bigger. So x is all real numbers. Well, there's no gap along the x-axis then. So it can't be one of these hyperbolas. Okay? So that's not possible because x is all real numbers. So what's happening along the y then? If I test what's happening along the y, I get y squared is equal to x squared, and I'm going to move the 4 to this side, so it becomes plus 4. Well, now we start getting restrictions because the smallest that this side can be is 4, because x squared can't be negative. So y squared must be bigger than or equal to 4. Well, if that's the case, then y must be bigger than 2, or if it could be negative like 3 squared, which would be bigger than 4, so y can be less than or equal to negative 4. So now we have a gap, or sorry, negative 2. Now we have a gap on the y. Okay, it can be here, it can be here, and it can go down like this, up like this, up like this, for all real values along x. Yeah, that's going to be okay. But now we have this gap in here, and notice that the gap width, this is going to be the a value. If a squared is 4, a equals 2. And so now we can see that, oh, this a value again is related to the radius of a circle. It's the distance from the center to the vertex. Okay, now with circles, everything's contained in here. Now with hyperbolas, it just goes the opposite way, actually. So my vertices are going to be at, in this case, I'm just going to do this red. My vertices are going to be at 0, 2, and 0, negative 2. That's where my vertices are. Okay, so that's going to be 0, negative 2. That vertex is at 0, 2. The asymptotes, well, if I want to know the asymptotes, I can just solve for this y again. Y equals square root x squared plus 4. Well, again, I can see that plus 4 as x goes really big, so I'm going to do something called a limit. As x goes to a really big number, this essentially becomes x squared, square root of x squared, which becomes just basically plus minus x. So our asymptotes are again the same. It's going to be just a linear function with slope of 1. And in fact, again, if you notice what I did last time, I drew a little box with kind of a radius a. And if I did the same here, the diagonals of that box generate my asymptotes. And that's something that we're going to start using. This idea that I can use my my vertical radius and my horizontal radius to generate this box, which generates the diagonals of my asymptotes. So my asymptotes are going to be y equals plus minus x. Okay, so here are some generalizations then. We have two different types of hyperbolas. What we call a trans x, or where this axis, the hyperbola lies along the green axis here. So this is what we call a trans x-axis. And these types of hyperbolas, so these are where x squared minus y squared equals positive a squared. This is when x squared minus y squared equals negative a squared, or we can flip it around and make it positive. This, when we have it in this form, it's now a trans y. So the vertical line here is where the hyperbola lies along this time. Okay, so it lies along there like that. And I have these asymptotes are going to end up being the same because the x and y proportions are actually going to be the same as a circle, or it's going to be square proportion. So we're going to end up with these diagonals are just slope of 1 and negative 1. So when we graph a rectangular hyperbola, we need to know a few things. We need to know the coordinates of the center. We want to know the vertices, okay? And we can use the a value to locate the vertices from the center, okay? Because essentially it's like a radius. And we also need to know the asymptotes. So if I know those three things, okay, so if I draw a center here, and my vertex is here and here, I know my asymptotes are like this, okay, I know how to draw my hyperbola. Those are the only three things I need to be able to draw the proper hyperbola. I don't need a whole bunch of details. I don't need all these other points. I need to be familiar with the hyperbolic shape so I don't make some crazy looking shape. But other than that, these are the only three things I need to be able to draw my hyperbola.